Hello everyone, my name is Daksh and today I am going to present you my computer architecture project in which I had to design a processor which I named it as a Pikachu. So it is a single cycle dual core processor. So let me start with the problem statement. Our task was to design, model, simulate and test an application specific processor for cryptographic block cipher algorithms, more specifically towards IDA algorithm, that is International Data Encryption Algorithm. We were given certain constraints. One of the constraints was that we had only 14 types of instructions available to use. The memory must be in hexadecimal format. Each line in memory should be 32-bit wide, and we had to test the entire code for 1024 bits of data. Before explaining the IDEA algorithm, let me explain you what is a block cipher. A block cipher is a method of encrypting a text in which you require a cryptographic key and an algorithm that is applied to the block of data. So when the key and algorithm is applied, your data is encrypted. Some of the example of block ciphers are IDEA, SEED, RC2 and RC5. But we will only focus on IDEA. An IDEA is an encryption algorithm which uses a block cipher as above, and it has 128 bit of key and it is considered to be very secured. So let us understand how do we implement the IDEA algorithm. The data is of 64 bits and we divide them into 4 quarters each of 16 bit. You require 128 bit key which you divided into 52 subkeys. For encrypting 64 bit of data, you require 8.5 rounds. The first 8 rounds are similar to each other and you require 6 subkeys in each round. So for 8 rounds you require 48 subkeys and the remaining 4 subkeys are required in the next half round. Now the IDEA algorithm gets its security because of the interleaving operations from different groups like modular addition, modular multiplication and XOR. So this is the pictorial view of the IDEA algorithm with keys and data and different operations performed. So you might wonder, why do you require such type of an algorithm? Well, there are numerous applications. Some of them are in financial services, broadcasting to government. Data encryption can be used to protect the data transmission and storage. Security is required in smart cards while you email through public network and while sending the sensitive financial data. So this is the flow of my project. First I implemented the IDEA algorithm in assembly language using a Mars simulator. Then I generated a scripting code for all my instructions, registers and labels in Python. After that I decided the architecture of my processor, then I implemented it in Python, then I optimized it and then I compared it with other processors. So after understanding the IDEA algorithm, I implemented it in assembly language using Mars simulator to check whether it is correct. So I required 62 instructions in order to encrypt the 64 bit of data. This is the pictorial view of some of the instructions that I used and the corresponding number of times that I used. After the assembly code, I generated a scripting code in Python for all my instructions that I used in the assembly language. So now it is time in order to decide which type of processor do I need to select. So I enlisted some of the processors like single cycle, multi-cycle, single cycle with 2 cores and single cycle with more than 2 cores. So in order to decide from one of them, I enlisted some of the parameters like code size, throughput, latency, cost and complexity. I graded them based on these parameters and then the final result showed that the single cycle with 2 core processor scored the highest, so I decided to go with it. So hence Pikachu is a single cycle multi-core processor. So this is the high level diagram of my processor. I am using 2 cores identical to each other. Each core has its own register file, instruction cache and data cache. The instruction memory and data memory are separate for each of the cores. Since the instruction and data are very small, I am assuming that at the start of the program, all the instruction and data from the memory are dumped into the cache, and at the end of the program, the instruction cache and data cache dumps its data again into the data and instruction memory. Now let us understand the microarchitecture of my processor. The instruction memory will fetch the corresponding instruction depending upon the program counter and decode it. The decoded instruction is given to the register file where it gets its corresponding value and then it is given to the ALU. The ALU will do its corresponding operation depending upon the control signals given by control unit. Then the ALU result is either given to data memory if it is a load or store operation, or it is written back again to the register file for R type of operation. The program counter is then incremented and we get the next instruction. Since I am following MIPS architecture, I have three types of addressing mode, R, I and J. The instruction format of my processor is shown below. I am using 4 bits for opcode, 5 bits for each register operand, 10 bits for the immediate value and 3 bits for label. Consider the example add D1, B1 and K1. So the 4-bit opcode is stored here. The register opcode are stored over here. Since it does not have immediate value and label, so we append it with zeros. Below are the instruction format for branch, jump, halt and label. The halt and label only has 4 bits opcode followed by all zeros. Following is the instruction summary. I am using 14 types of instruction which are shown below and their corresponding opcode values. The 21 registers that I am using and the corresponding register code is given below. And here is the label summary with 5 labels along with their label code. So now let us consider an add example. From the previous slide we have seen the opcodes for each of them. So the opcode for add is 0001. The corresponding opcode for each register is stored. Since it does not have an immediate value, we give it zeros and no labels again zeros. So my instruction code for add D1, B1 and K1 is following and its corresponding value in hex is this. Let's try to understand the same example at microarchitecture level. So consider the PC is given and the corresponding instruction is fetch and then it is given to the decoder. In decoder we find out that it is an add instruction with 3 register operands. So the decoded instruction is given to the register file where we get the values of register B1 and K1, which is then given to the ALU. The control unit tells us that it is an add operation and then we perform add operation on the values stored in B1 and K1 and store it in ALU result. This ALU result is then again given back to the register file to store at its destination register, that is the D1 register. Now after this instruction has been completed, the PC is incremented by 4 and we can fetch the next instruction. So all the black lines shows us the control path of this add instruction. Following is the performance analysis of my processor. Since it is a single cycle processor, all instructions will be executed in one cycle. I am assuming time required in each of the unit like fetch, decode, ALU, data memory and register write. So I am calculating the total time required to execute one instruction. So as you can see, the R type of instruction requires the maximum amount of time, that is 42 nanoseconds. So each clock cycle will be of 42 nanoseconds. So you might wonder why you require 21 nanoseconds for the ALU operation. The main reason is the multiplication modulo. It is the most critical path of the IDEA algorithm. I am assuming a special multiplier algorithm called as the Montgomery Arc2 Vera 4, which does my modulo multiplication in 21 nanoseconds. Then calculating the time for the other units, I find that my R type of instruction takes 42 nanoseconds, hence it is the critical path. So now let us take a look at performance analysis. So I require 2100 instructions to encode my entire 1024 bits of data. I am getting a throughput of 11.6 Mbps and the latency is 5.5 microseconds per round. Since it is a single cycle processor, the CPI is 1. The following is a graph of the throughput versus data size. So as you increase the data size, the throughput also goes on increasing. Following is a graph of throughput versus number of cores. Since I am using multi-core processor, my throughput is around 11.6. So as you goes on increasing the cores, the throughput also goes on increasing. But the trade-off is that the cost as well as the complexity and the power consumption will increase. Now let me enlist some of the special features of my processor. Initially I started with a single cycle processor, but the throughput was very less. Hence I decided to optimize it. So now I am designed a single cycle dual core processor which actually doubled my throughput from a single cycle processor. I am also using an instruction and data cache which saves the latency and delay. I am using a special technique in my code to do modulo addition which has saved millions of iterations. I am using a special algorithm for my modular multiplication which saves millions of cycles again. After writing the assembly code for my idea algorithm, I implemented and simulated in Mars in order to check its corresponding correct values. I also generated a scripting code in Python. The scripting code is a generic, so if you add any of the 14 instructions and the registers that I use, it will automatically produce the corresponding instruction code. Also, I am doing parallel operation in both the cores for my data as well as instructions. For literature review, I am comparing my processor with 3 other processors. The first processor is a VLSI implementation of IDEA algorithm. It has a throughput of 177 Mbps and the system runs at 25 MHz. The high throughput is due to pipelining and 4 modular multi. The second processor is a high performance FPGA implementation of IDEA algorithm which has a throughput of 500 Mbps, and the last paper also presents a VLSI implementation of IDEA with an encryption rate of 355 Mbps. Here I am comparing my processor along with 3 other processors based on throughput, latency, number of transistor, cost and power. Although all the 3 processors have very high throughput and latency, but my Pikachu has very less number of transistor count, cost as well as power. Hence you can say Pikachu is a low cost, low power processor with a reasonable throughput and latency. I would like to conclude by saying that I successfully implemented the idea in assembly language using MIPS Mars simulator. I also implemented a scripting code in Python to generate all the instruction codes. I successfully implemented a single cycle dual core processor with realistic throughput and latency. Dual core is the highlight of my project, which doubles the throughput. The power consumption is really less, and I am using special techniques for modular addition and multiplication. References that I use and paper references. Thank you.